assuming that the heater stays at a certain temperature, the flow rate is steady, right, through the device, we would see continuous deposition onto that resonator. And as we continuously deposit the mass, right, the frequency, the rate of the change of the frequency would be constant, right? And in this case, of course, would be negative, right? So this is why we have a minus sign here, because the frequency would actually go down. And so if we did when we overlapped essentially the two graphs, and you can see there's a very good correlation between the ground truth data from Dastrek and the rate of the frequency change of our resonator. We did some analysis on this, and based on the noise level here, it looks like our low limit of detection is in single micrograms per cubic meter. Okay, so that's fairly sensitive for this size of the device, right, compared to say optical methods. In fact, it's sensitive enough that you can use it as a detector for the EPA standard. Let's say 12 micrograms per cubic meter yearly averages, right? So it's a fairly sensitive detector. And again, in this case, we haven't really optimized the flow path yet. This is what we're doing now. So we're really happy with these results. So it works nice with tobacco smoke. We did the same experiment with diesel exhaust, and basically you can see the same correlation. So it works with diesel exhaust PM as well. Okay, and again, it depends on the integration. So that integration time, so that single microgram per cubic meter, that requires at this point about 10 minutes of integration time. Okay, if you integrate it for less, it's a little bit less sensitive. Yes.
So the dust track is optical, and it probably isn't very responsive to the very small particle scattering there.
Right.
Whereas presumably your mass sensor, I guess small particles don't add a lot to mass, but it does respond